All right, young friends, welcome to podcast 8 in our ecology unit. In this podcast, we're going to be looking at various aspects of discussing population growth. We've talked about how to describe a population, but usually what scientists are looking at when they are looking at a population is changes in that population over time, not just describing it as in a single stagnant point in time. So that usually implies some kind of growth. Now, be careful because growth doesn't necessarily, we can be talking about an increase in population. Perhaps we should talk about population change over time because that really is the bottom line. We talk about population growth, but change in numbers over time is really what we're talking about. And that's really an important little equation. We'll use it a ton in this class. It's basically a rate calculation, and you should be aware of how to do that. We can use it in many different circumstances. So we can talk about, therefore, an increase or a decrease in population size. Increases in population size generally are due to two things in a population. Either more organisms are getting born in that population, so birth, we would usually refer to that as the number born would be referred to as a B variable. And immigration, those individuals, how many different individuals migrate into this population from outside of it. So immigration, the I, into. Okay, so, and that's, here we are in our little picture, birds flying in from somewhere else or else getting born into this population. Now, decline can also happen in a population. Of course, death, mortality, you die, that's going to reduce your population size, obviously, but also if individuals leave your population and go to some other population, that will reduce your population size. So emigration, I like to remember it, E is with exit, you're going to leave the population. And for all of these, you would measure it over some period of time. Did these numbers change? Did the number change from when you started to when you finished monitoring the population? Okay. Now, there are two basic models of population growth that are discussed. One is a little, well, let me not say that. One represents growth that would occur in ideal conditions, meaning the population had unlimited food, unlimited space, unlimited shelter, everything they needed, no predation, just everything they needed, no resource limitations, okay? And this is generally referred to as exponential growth, okay? The other type of growth kind of is a more realistic situation where you don't have unlimited food, you don't have unlimited space. Things are going to limit your ability to just reproduce wildly, okay? Now, exponential growth, generally speaking, produces a growth curve. If you were to plot growth over time, so here's your population size on your y-axis. Let's remember our axis. Boy, that doesn't. Y-axis, and your time is going to be on your x-axis. And over time, we can see that the population number is just going up, and what we see is it starts out with fairly slow growth. Takes it a while to get going, but once it gets going, this growth just shoots up. It dramatically takes off and starts escalating very, very rapidly. That is a typical J-curve, exponential growth curve. Now, in a more realistic situation, what you have instead is you have your slow growth to begin with, which we see here, and then you take off and start reproducing lots. Once you get to a certain number, you can really, the exponential growth just takes over and you're reproducing like crazy. But at some point, there is just a limit as to how many organisms in this population, this environment can support. And when we've hit that number, the maximum number that this environment can support stably, that is carrying capacity. We are said to have reached carrying capacity. Maybe carrying capacity for this imaginary population in this environment is 1,000 individuals, and if we have more than 1,000, the environment can't support it, so those individuals start to die. And so we're going to just level off at this right around this carrying capacity level. Okay, so exponential growth then. Basically, we presume that we're just going to indefinitely keep growing. We know that's really not possible, but the growth appears to continue indefinitely, at least in the graph, and we assume no resource limitation. This is an equation that is generally used to describe exponential growth rates. We are going to talk more about the equations later. I'm just showing that to you now. We'll catch up with those in a little bit. Okay? I'm going to touch on logistic growth again, but let's talk about this. So there's our exponential growth curve. It's just going to shoot straight off into orbit, okay? Just reproducing organisms like crazy. Once we get past this slow point, eventually you get enough members of your population that as they all reproduce, you just get this rapid growth that really takes off. Now, we know that can't go on forever. So what kind of things do affect population growth? There's all kinds of things. Abiotic factors, things that are not living, can affect population living biotic factors. How much sunlight is available is going to affect plants, which then will affect other populations. Temperature, precipitation, how much water is available, what kind of nutrients are in the soil. And of course, other biotic factors can affect various populations. Are there lots of predators? Is there enough prey for a predator to eat? Is there competition for a food source? Are there parasites, diseases, whatever? All of these things, all of them can either contribute to enhancing population growth or suppressing population growth, depending on the situation. So there's a whole lot of stuff that can affect that. So these things that affect population growth we refer to as limiting factors. These are things that can limit population growth or encourage it, I suppose, but generally we refer to them as limiting factors. If you have enough of a particular nutrient, then your population can keep growing, but if that nutrient is taken away, then your population can't keep growing, and the absence of that nutrient is going to limit population growth. It's a limiting factor, okay? There are two types of limiting factors. There are density dependent and density independent. What does that mean? Density is referring to how dense, how populous your population is in a given area. So here's my area and here's my population. Here's another area and here's my population in that area. All right, we're going to call this population A and population B, which is more dense, population B. Now, density dependent limiting factors are going to have a greater effect as the population gets more dense. That is, they are density dependent. The limiting factor is only really a problem when the population gets really dense, lots in the area. Density independent limiting factors mean that I don't care if you're this population or that population, this limiting factor can affect you basically the same way, okay? So let's look at these examples of some of these. Density dependent. The more organisms in the population, the more dense, so we're talking about, whoa, we got all these guys in this population here. The more limiting these factors become, and the more effect these certain limiting factors are going to have. For example, the more critters you have in your population, the more they're going to compete. Remember, members of a population are competing for the same things, the same food, the same mates, the same kind of habitat nesting sites, things like that. So, competition is going to be huge. Parasites and pathogens, diseases that can get passed from one to the other to the other. If you've got more, it's just like living in a city. disease is going to run more rampant through a city than it is through the open countryside, because people are passing germs amongst each other because they're living in such close proximity to each other. So these are things that limiting factors that get worse or more limiting the more organisms you have in the population. Okay, so the more critters you've got, the more limiting the limiting factor is. Now, a density independent, I don't care, again, if I am in this population or if I am in this one, this kind of limiting factor is going to have an effect on my population, okay? A tornado. If a tornado comes through here, they're all dead. If a tornado comes through here, they're all dead. It doesn't matter how many were there or how many weren't there. In this population, going back to the density dependent limiting factors, all right, viruses are not going to spread between these three guys very easily because they don't come in contact with each other very often. But viruses would pass very readily from these guys because they're living in such close proximity. There's so many of them. So in this case, a virus wouldn't be such a limiting factor on this one, but it would be pretty devastating to this population. But here, a tornado, it doesn't matter how many are in the population. So that's a density independent. Doesn't matter how many's there. Some of these you can argue about. For example, I see that, and I would argue about that, because if you've got lots of plants, the ones that are up high are going to start limiting the light that's going to get to the ones that are down low. So I would argue that that one is actually a density dependent. However, if the sun goes out, everybody's going to die. So, you know, it's kind of depends on how you look at it. All right, but my best example to think of is a tornado that's going to wipe out everybody, and that kind of helps to give us a concrete example. A forest fire, that's going to come through, and I don't care if it's a big population, small one, everybody's going to be affected by that. A tsunami, that's going to affect everyone, okay? All right, carrying capacity. Now this is going to take us back, this part of the discussion. So if we have these limiting factors, so we've talked about our J curve, jump, but now we know, yes, there are factors that prevent the curve from going up forever that are going to cause the curve to flatten out and make this logistic growth curve. And when we hit that flat part, that is carrying capacity, or K, okay? Carrying capacity, you should know the definition, the maximum number of individuals of a particular population that an environment can support. And again, what the carrying capacity is for a particular environment depends on what resources are available. If an environment has lots of resources, its carrying capacity is going to be higher than an environment that does not have very many resources. Okay? So again, here's your logistic growth model. We've already talked about that. Again, another calculation, just a fancy rate calculation really, but we'll talk more about this in a bit. Okay? All right, so this is just showing you actually the J curve, the exponential and logistic growths compared on the same graph. No control, limiting factors and no limiting factors. Okay? All right. We will talk. I don't want to go into this online. You'll go crazy. Maybe I'll do a separate podcast. But the calculations, this will be available to you. You've got your handout with all of your calculations on it. Or you will once you get in class. I will give you that. This is important right here. This is just a basic rate calculation. So change in your data value, whatever. In a population, you're usually talking about numbers of organisms. So change in whatever data value you're measuring over change in time. That's a basic rate calculation. You ought to familiarize yourself with these values. Again, these will be on your calculation sheet that I'm going to give to you. And these are the various calculations that we'll at least do a couple of examples of, so they won't be completely foreign to you if you should see them on an exam, okay? This is showing exponential growth with no limit. This is showing logistic growth with a limit, and that is putting that limit of carrying capacity on there, okay? We'll talk more about that in class. Let's just move on right now. Now, it is important to understand that stable populations typically oscillate around K, and what I mean by that is if this is my logistic growth curve and this is carrying capacity right here, my population isn't going to be perfectly flat along carrying capacity. It's going to rise and fall, rise and fall, rise and fall, rise and fall, and it's going to hover around that, okay? These are generally called kind of like a little boom and bust cycle, and some boom and bust can be very dramatic, but many kind of oscillate around this carrying capacity value. So usually these oscillations are caused by interactions between predator and prey, population cycles of predator and prey. Okay, let me erase here. Hold on. Coleman. Erase all ink on slide. Yes. All right. This is the classic. You may have seen. Well, if you freshman year, I'm sure you don't remember. This isn't exactly riveting stuff here, but I know I show this to everyone, and I'm sure other teachers do too. This is showing the populations of these snowshoe hares, that poor little guy right there, and their population over a number of years in the area where they were being studied, okay? And we see that it oscillates. But what we see is the lynx, which is that guy, bobcat, right there, kind of tends to oscillate with them. As the hare population goes up, what would happen to the population of the animals that eat hares? Well, they would go up because they'd have lots of food. But if these guys get too many of them in the area, then they overpredate the hare and the population kind of crashes because all the hares get eaten. Well, what happens to the lynx? As they eat too many hares and their population crashes, these guys do too. So what we have is a situation where as one goes up, the other goes up, but as the predator goes up, he might go up too much and bring down the hare, which is then going to bring down the predator. So what you see is this: I'm going to go up, I'm going to come down, and my predator is going to follow me, just maybe lagging behind just a little bit, okay? So that's why we get this curve. They are definitely related to each other, okay? But if you'll notice, carrying capacity for the population of the hares hovers right around here. Carrying capacity for the bobcats hovers just below that, okay? All right, are there times when exponential growth with no limit, does occur? If you are introducing a species to a new environment, for example, like an invasive species that's not supposed to be there, for example, the northern snakehead fish, it's fish they're concerned about up in the Potomac, but other places as well. It's a crazy predator, it's not supposed to be here, and its numbers are going up. It has no known predators in the Potomac River, and it's gobbling up everything. It's great habitat for it, so its numbers are just exploding. Lionfish off the coast of the Atlantic have been released by people who have aquariums and get tired of their lionfish, and they release them. And now these lionfish have no natural predators, and their population just booms, it explodes. So in those cases, we do see J-curves. So invasive species are associated with a J-curve. Would they eventually level out once they consume everything in their environment? Sure. But right now what we're seeing is this explosion in certain invasive species as they just take off, and we don't know what limiting factors are going to control them ultimately. And will they have decimated our environment in the meanwhile? Also, species that are rebounding from catastrophe, near extinction, if we can help them, we can watch their numbers go up if it's not too late. African elephants protected from hunting, we've seen their populations go up. Not that they're not still threatened, but we are seeing that population go up. Whooping cranes as well. Again, look, these numbers are not huge by any means. We're talking 200 individuals, but we're seeing that as an exponential rise from less than 20 individuals, okay, over the period of time. There are other factors that affect how fast a population can grow, how many males versus females. The more females you have, typically, a male can fertilize many females, but a female generally is the one who has to raise the young, so your population is kind of going to depend on how many females you have. It's very important to protect the females more so than the males if a population is struggling. Another factor, how long does it take for those females to reproduce? How many times can they have a brood in a season? Can they just raise one baby, or can they raise multiple litters, and so on? Age structure is referring to what age females can begin having babies, and how long of their lifetime they can continue to have babies. The earlier and the longer, the more population growth potential there is, the longer you have to wait for an adult to mature. That limits how fast your population can grow, okay? You ought to know what this word means. Demography is simply studying factors that affect population growth. We look at different statistics, how many are alive, how many die, how many males, how many females, and so on. We do this a lot with humans. You also ought to be able to read and understand an age structure diagram. This is going to be telling you a lot about the potential for growth in a population. Is this population growing or not? If you look at this age diagram, age structure, this is percent of population. This is the different ages. They've got males and females indicated by color. Not very many old people, but look at all these young people that are coming up. And eventually when these young people hit this bracket, they're going to be able to reproduce. And these bars that they create should just get wider and wider. So the wider your base means you've got lots of young people that are going to eventually be of reproductive age, and we're going to see that population explode. If what we see here is these slow growth to zero growth, declining, the base is narrower than the middle, so these people are not having very many children, and so that population is not going to be replacing itself, and so it should get smaller and smaller, okay? That's how you need to look at an age structure. The wider the base, the population isn't growing. The narrower the base, the population is either not growing or actually declining. Human population growth. Almost done, but you got to look at this. It's crazy. There it is. Slow growth. You can see this classic slow growth beginning, but what kind of growth do we see? We see this rapid rise starting after somewhere around this 1500 AD, and we just see it shooting up incredibly dramatically. That is the classic exponential growth. At 1650 year, we had about 500 million people. The Industrial Revolution and creation of agriculture and all that, and significant medical breakthroughs. And what we see is enormous growth. In 1975, there were 4 billion people. Took us this long to get from 500 million to 4 billion. Okay, so from here to here, but look how long it took us to get from 4 billion to 6.5, not very long, and now in 2012 we have about 7 billion, and it's just going up. We have not hit carrying capacity. We don't know what carrying capacity is, but we are adding about 200,000 per day, and that number will steadily increase as we have more and more people of reproductive age. Right now, or probably a few years ago, these are statistics that show you comparatively how many people are in some of our most populous countries. What caused this crazy exponential growth? Well, we already kind of mentioned it, the Industrial Revolution, medical breakthroughs and so on, agriculture, being able to farm and things like that made the difference. What's carrying capacity? We don't know. Something to think about as we're looking at that. We are not, as you can see, we are not the most populous nation, okay? China and India both have us beat. But look at this. Look how little consumption people from India, how little, this is showing you how many acres of land are required to support an individual. 2.6 acres. To support our lifestyle, 30.2 acres. So by far, we are using way more of the world's resources than India is, but India has us way beat in terms of sheer population. Do those people in India want to have our standard of living? Sure they do. Could our world support that? Imagine all those people living at our standard of living. We have a huge ecological footprint, each of us in this country. We use an enormous amount of resources, something to think about. So, the wealthiest 20% of the world consumes 86% of the resources. 20% of the people consuming the vast amount of resources of the world, and not to mention releasing more wastes, CO2 in particular. So, there we go. That's it. I know that was long, but that's kind of a tedious little section. Thanks for watching. I will catch you in the next podcast.